Hello. In this video, I'm going to solve some homework problems from section 8.6, representation of functions as a power series. This is a section where we explore, in essence, how to build a power series for a function if it's based on a function that we already know the power series of. For example, we know that 1 over 1 minus x can be rewritten as 1 plus x squared, etc., i.e. we can write that as sigma n equals 0 to infinity of x to the n. And we're going to make use of that as the root for several of the problems that we're going to solve. And then in the examples for the book, for the section, they give us the power series for inverse tangent of x as well. They tell us that inverse tangent of x is equal to x minus x cubed over 3 plus x to the 5th over 5, etc., 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 or what we can write as sigma n equals 0 to infinity, negative 1 to the n, x to the n over n. Now, it's not x to the n because we need the odds, so we're going to make this, to get our odds, remember we make this 2n plus 1, and down here we're going to then have 2n plus 1. So those two series, along with the series for the natural log, which they also give us in the homework, and I'll write that one down, or they give us in the examples, I'm sorry. It's in example 6. We'll need that one to do one of the homework problems as well. So in this section, if you look through the examples, I guess that's going to pay dividends for you. So we'll start with problem number 8. Problem 8 comes from a set of problems that says find the power series representation for the function and determine the interval of convergence. Now remember, we have a rule, a theorem that says if we integrate or differentiate a power series, we don't change, right? We don't change the radius of convergence, but we may change the interval of convergence. So in problem 8, just looking at problem 8 here, the function they give us is, they give us f of x equals x divided by 2x squared plus 1. And believe it or not, we're going to try to make it look like this, right? So we can pull an x out. That turns it into 1 over. We want the 1 to come first, so we have the 1 here. So I'll take this 1 plus, and then we have 2x squared. Now, we need this to be a minus, right? This needs to be a minus. So we're going to rewrite this again. We'll write it as x. We'll keep our 1 on the top. And we're going to write this as 1 minus. And then, of course, two negatives make a positive. And so we're going to get minus 2x squared inside. So the way we build a power series from another power series is we look at the root and we say, okay, when this is x, this becomes x squared, this becomes x to the n. Well, playing x for us in our version is going to be this. Our x is minus 2x squared. So we, therefore, can say that this x over 2x squared plus 1 is equal to, and now we're going to take this and write it using this power series. The x on the outside we just leave alone. Now, what is this? Well, this is our x. Our x is minus 2x squared. So we're going to put that right here in place of this x. So we're going to get sigma n equals 0 to infinity. And instead of x to the n, we're going to get negative 2x squared to the n. Now, from here, we're going to do some just basic arithmetic, right? This is -1 to the n. This is 2 to the n. This is x squared to the n. This power of n is applied to the -1, it's applied to the 2, and it's applied to the x squared. So we can rewrite this. We'll just leave the x outside for now, and we're going to put our sigma here. N equals 0 to infinity. And I'm going to go ahead and write this as -1 to the n. So it looks like an alternating series. We have our 2 also to the nth power. So we have 2 to the n as another factor. And then we have x squared to the n. That's going to be x to the 2n using our rules of exponents. But don't forget, we have an x to the first out here that we're going to multiply in here. So when we take this x to the first times this x to the 2n, we're going to have one more x. So our final solution then is going to look like this. N equals 0 to infinity, -1 to the n, 2 to the n, x to the 2n plus 1. Now, we know this converges, right? We know it converges. And this, if we write this out, I'm not going to go through the trouble of writing this out, but if we write this out, this turns out to be geometric, right? We know this is geometric. And so since this is geometric, and all we've done is replace each of these x's with a -2x squared, I mean, after all, this is geometric. R is equal to x. A is equal to 1. So over here, if we put 0 in here, right? If we put 0 in here, so we could write all of this out. We're not going to go through that trouble. We replaced our x with -2x squared. So our r, right? Our r, remember this converges when the absolute value of r is less than 1. But for us, our r is -2x squared. And so we can put that in here. Now that becomes, by the rules of absolute values, that just becomes 2x squared is less than 1. Because remember in the homework directions, it's to determine the interval of convergence. We're going to divide both sides by 2. That would get me to the absolute value of x squared is less than 1/2. And then when we take the square root of both sides, right, we're going to get the absolute value of x is less than 1/√2. So if we wanted to write our interval of convergence, right, right now we have -1/√2 is less than x is less than 1/√2. And so that's problem 8. The next problem I'm going to work on, I'm going to try to focus on some of the even problems because I figure the answers to the odd ones are in the back of the book. So we'll take a look at problem 14. 14 has a different set of directions. It says find the power series representation for the function and determine its radius of convergence. Okay, so what do we know in problem 14? Well, the function they give us is f of x equals, and we have x squared inverse tangent of x cubed. Now we have inverse tangent of x. We know the power series for inverse tangent of x. So if we just focus on this part right here, if we just focus on this part, we could find that part and then multiply by x squared at the end. So we're going to just say that this is equal to x squared times, and then the power series for inverse tangent of x cubed, we're going to use this, but we're going to replace our x with x cubed. So we have sigma n equals 0 to infinity. So it's just a fancy substitution problem, right? We're going to put x cubed here. We're going to put x cubed right there. We're going to put x cubed right there. Well, we don't want to do it term by term by term. We're just going to put x cubed here. So we're going to have -1 to the n. Then our numerator is going to be x cubed, and the exponent is 2n plus 1, and then our denominator is 2n plus 1. Now, if we simplify that, right? If we simplify that, what can we find? Well, we can find by the rules of exponents that this is going to be 3 times 2, that's 6n. 3 times 1, that's 3. So we're going to have our x squared on the outside. We're going to have sigma n equals 0 to infinity. We're going to have negative 1 to the n. And then from here, using our rules of exponents from algebra 2, power to a power you multiply, we're going to have x to the 6n plus 3, all divided by 2n plus 1. Now, the only thing we have left to do now is to incorporate this x squared into here. That's 2. This is 6n plus 3. When you multiply x to a power by x to a power, you add the powers. And so we get our final answer, which is sigma n equals 0 to infinity, negative 1 to the n, x to the 6n plus 5, all divided by 2n plus 1. From here, we'll work on 23. Let's do, no, I'll do 21. Let's do 21, because it has a different set of instructions. And so it says, find a power series representation for f, graph f, and several partial sums on the same screen. What happens is n increases. All right, so here, I'm not going to be able to graph for you, but we can find the power series representation. And then we can talk about what the partial sums look like. So f of x equals, and here we have the natural log of 1 plus x over 1 minus x. Looking at this problem, I may not have enough room here on the remaining portion of my whiteboard to work this out, but we know, we'll give it a shot. We know from our rules of logs that this is the natural log of 1 plus x minus the natural log of 1 minus x, right? That's just our log properties from algebra 2 and from pre-calc. Now, they gave us in example 6, right? In example 6, they told us what the series was for the natural log of 1 plus x, this one right here. So from example 6, they told us that the natural log of 1 plus x, and they found it for us, right? They found it for us in example 6. They said, hey, you know what? That's the integral of this. The integral of this is the natural log. We know the series for 1 over 1 plus x. Right? We haven't written it down over here in our little table, but we know the series for 1 over 1 plus x, because to do 1 over 1 plus x, we would make this 1 over 1 minus x. And so therefore, just squeeze it in over here, 1 over 1 plus x would be 1 over 1 minus x, right? That's what that would be. Now, we know from up above that that's going to be sigma n equals 0 to infinity. And our x here that's underlined in blue and has this arrow pointing at it, our x is minus x. So we would have minus x to the n. And that gets us sigma n equals 0 to infinity minus 1 to the n x to the n. Right? That's what that becomes. Now, if we had to integrate this, right? If we had to integrate this, because that's what it tells us to do here. It tells, remember, this is just this piece right here. To get the natural log of 1 plus x, which they gave it in example 6, but we're just building it here for more practice. To get this, we would integrate this. So if we integrated 1 over 1 plus x dx, we know we get the natural law, but we're looking for the power series representation. That would be the integral of sigma n equals 0 to infinity, -1 to the n, x to the n, dx. That would get us, when we integrate this, we're going to get sigma n equals 0 to infinity. We're going to get -1 to the n. That's just a constant. We're going to add 1 here. That's going to be x to the n plus 1. We're going to divide by n plus 1, and we're going to get a c. Right? Now, remember, to find c, all we do is plug a value in here and a value in here, and we can find c. Right? All right, so all of that was just because they already did the work for us, right? They already did the work for us in the problem in example 6. So they told us this series right here was equal to, when they did the work for us, they told us it was equal to x minus x squared over 2 plus x cubed over 3, right? And this is what we would have gotten right here if we would have just plugged our numbers in. We did the work as well. And then they get minus x to the 4th over 4. And we'll just write one more down. It's going to be x to the 5th over 5. Plus our c, right? Our c that we got over there by integrating. Now, if we try to write that down, right? If we try to, let's get the c out of the way first. If we put a 0 in for x on this side, we're going to get natural log of 1, right? Natural log of 1 is 0. So if we put 0 in for x, we're going to get 0 here. If we put 0 in this for x, well, all of these x's are going to be 0. So every term in this series is going to be 0. So on this side, right, we're going to have natural log of 1 plus 0. On this side, we're going to have all these terms are going to be 0, or we're going to have plus c. Of course, the natural log of 1 is 0. So that gives us c is 0. So when we do this, our c is equal to 0. So that's the natural log of 1 plus x. Now, what are we going to do? How are we going to find the natural log of 1 minus x? Well, we're going to do the same technique we've done everywhere else. We're going to use this and the fact that we know its series, and we're going to let x be minus x. Because remember, the natural log of 1 minus x is really the natural log of 1 plus minus x. So we're just going to call this x minus x, which means we can come over here to the series representation and we can put in minus x everywhere there's an x. Or we can come over here to how we wrote it out here because we copied it from example 6, and we can put a minus x every place there's an x. What does that look like if we do that? Well, don't forget we have this minus sign right here. Now, everywhere here that there's an x, we're going to plug in minus x, right? We're doing this substitution right here. So this is our friend x in the positive side, but in the minus side, that becomes minus x. So we're going to put a minus x right there. Now we're going to put a minus x in here and we're going to square it. When we put a minus x in here and square it, that just becomes x. Now we have the minus sign. So we're still going to get minus x squared over 2. And just as an aside, what happened there? We had x squared over 2, right? That's what we had with the plus, but we're doing minus. So this is what we had. Well, what happens when you square negative x? You get x squared over 2. So that's what I got here. Now, why is there a negative? Well, because there was a negative over here in our original series. There was a negative, so we kept that. Now, what happens with x cubed over 3? Well, we're going to have minus x cubed over 3, aren't we? And when we cube the negative, that's going to give us minus x cubed over 3, because 3 negatives make a negative. So there's a plus in front of it in this version, but over here we have a minus, so that's going to be minus x cubed over 3. Now, there's nothing about x to the 4th that's special. It's even. X squared was even. So it's going to turn out to be positive once we take the negative x to the 4th power, but it presents a negative out in front, so that negative is going to stay. Here we have x to the 5th, negative times negative times negative times negative times negative. That's going to be negative. So that's going to be a minus x to the 5th over 5. So each one of these terms is going to be negative. Now, we were asked to find this. Okay, we found the power series for this version. We had to use our log property first. Then we found the power series of this version just using our substitution technique. And so now what do we have, right? Where are we from here? Well, we're going to put these two things together. This is an x. That's minus x. So I have x plus x down there. Here I have minus x squared. Here I have minus a minus x squared. That's a plus x squared over 2. So those cancel, right? Those are gone. They cancel. Here we have a x cubed over 3. Here I have a negative x cubed over 3, but another minus. So that's going to give me plus 2 x cubed over 3. Here I have a negative x to the 4th over 4. Here I have a negative x to the 4th over 4, but I'm subtracting, so that gives me 0. Here I have x to the 5th over 5. Here I have negative x to the 5th over 5, but with a negative sign. That's going to give me plus 2. Wow, pen blew up. That's going to give me plus 2x to the 5th over 5. And it's just going to keep going like that. The next term, the 6's are going to, x to the 6 is going to cancel. I'm going to get 2x to the 7th over 7. And it's just going to keep going in that manner. Well, what is that going to equal? Right? What is that? Now, remember, this is 2x to the 1st over 1, right? 2x to the 1st over 1. So we can write this, right? We can write this as a series now. So it's going to be sigma, right? Everybody has a 2. So we're going to have sigma n equals 0 to infinity. We don't have any negatives. All the terms are positive, so we don't need a negative 1 to the n. We're going to have a 2 in the numerator because everybody has a 2. The powers of x are going to be what? Well, we need 1, and then we need 3, and then we need 5, and then we need 7. That means we need the odds. So that's going to be x to the 2n plus 1. And then, of course, when it's the first power, we have a 1 on the bottom, the third power 3 on the bottom, fifth power 5 on the bottom. So then the denominator is going to be 2n plus 1 as well. And we were able to find a power series representation for the natural log of 1 plus x over 1 minus x. So if you wanted to find, say, for example, the derivative of this, well, that wouldn't be fun, right? First of all, it's going to have the quotient rule, it's going to have the chain rule, it's going to have the natural log rule. You could take the derivative of this, pretty simple. You just bring down the exponent and subtract 1. Right? the derivative of this is going to take a lot of time. But if someone were to ask us, for the derivative of the natural log of 1 plus x over 1 minus x, right, that's going to take a lot of time. But instead of doing that, we could just take the derivative of this. We could say, well, that's equal to sigma, right? It's going to be n equals 1 to infinity now, because the constant term is going to go away. When we put 0 in here, we don't get a constant term, do we? So I strike that. When we put 0 in here, we get x to the first. So our very first term here is, well, it's sitting right here, Kevin. It's 2x. When we take the derivative of that, we're going to get a 2, right? So that the 0 doesn't go away. So when we take the derivative of this, we keep the 2, that's a constant. We keep the 2n plus 1, that's a constant. This 2n plus 1 comes down. And we take away 1. That's pretty quick, pretty simple. I mean, if you know your power series and you can work with them quickly, they can actually speed up something you learned in Calc 1. All right, so that was problem 21. The next one I'm going to work on, I'm going to clean this off here. The next one I'm going to work on is 26. We'll leave that part over there for reference. So that was problem 21. We'll take a look at problem 26. Problem 26. Again, a different set of directions, and it's the even one in this grouping of problems. It says, evaluate the indefinite integral as a power series. What is the radius of convergence? Okay, so they want us to integrate the inverse tangent of x squared dx. Now, earlier, unfortunately, we found the power series for the inverse tangent of x cubed, didn't we? We didn't find the power series for the inverse tangent of x squared. But we can do that, right? We know what inverse tangent looks like. It looks like this. So we can write down inverse tangent's power series pretty quickly. This is going to be the integral of, and if we wanted to write down inverse tangent's power series, we just excuse me, the hiccups, we just make this x squared, right? X squared. So we're going to put x squared right there. So we're going to integrate sigma n equals 0 to infinity, right? And then what do we have? We have negative 1 to the n. Our numerator is going to be x squared, right? X squared to the 2n plus 1, because we're doing our substitution. And then our denominator is 2n plus 1. So this is our integral. Now, if we clean that up a little bit, right? If we clean that up a little bit, that's going to be the integral. This is going to be sigma n equals 0 to infinity, negative 1 to the n. We have x squared to the 2n plus 1 power to a power you multiply. So that's going to be x, 2 times 2 is 4n, 2 times 1 is 2, right? All over 2n plus 1 dx. Now, how do you integrate? Well, you add 1 and divide by the new exponent, right? The integral of x squared is x cubed over 3. So we're going to add 1. So this is going to get us the sigma n equals 0 to infinity. We're going to get our negative 1 to the n. We're going to add 1. So this is going to be 4n plus 3, right? Add 1 to 4n plus 2, you get 4n plus 3. Now, our denominator down here already had a 2n plus 1. That came from here. And now we divide by 4n plus 3. Right? And we can go plus c. So it said, what is the radius of convergence? That's what they asked us. Well, our previous radius of convergence for inverse tangent, they told us was the absolute value of x is less than 1. The radius of convergence was 1. And when remember the radius, the interval goes from -1 to 1. So the radius is the midpoint out. So the radius, right, this goes from -1 to 1. Here's the midpoint. So r is this distance right here. So for that, r was 1. Now, for us, we've replaced x with x squared. But fortunately for us, when we take the inequality, the absolute value of x squared less than 1, that just gets us the absolute value of x is less than 1. And so we get the same radius convergence. The radius of convergence is 1. So that's 26. I'll go ahead and do 32. I don't know how much fun you're going to have with 32, but I'm going to have a lot of fun with 32 because it involves a second order differential equation. So they give us a function. They give us a function f of x equals, and the function they give us, they represent it as a power series. It's n equals 0 to infinity. It's -1 to the n, x to the 2n divided by 2n factorial. Okay, this is the function they give us. And they ask us to show something. They want us to show that f double prime of x plus f of x equals 0. If you add the function and its second derivative, you get 0. And that's what they want us to show. So the easiest way to do something like this is just brute force. Just write down f of x. Write it down. Write down what f of x is. If you put a 0 in here, you get -1 to the 0. That's 1. You get x to the 0. That's 1. You get 0 factorial. Also 1. So you get 1. If you put 1 in here, you're going to get a minus. A 1 in here, you're going to get x squared. And a 1 in here, you get 2 factorial. So far, so good. Now, when you put a 2 in here, you're going to get plus. When you put a 2 in here, you get x to the 4th. When you put a 2 in here, you get 4 factorial. When you put a 3 in here, you're going to get a minus. You're going to get x to the 6th. And when you put a 3 in here, you're going to get 6 factorial. If you want to keep going and put a 4 in here, you're going to get a plus. You're going to get x to the 8th. And down here, you're going to get 2 times 4 is 8. You're going to get 8 factorial. And this is just going to keep going, isn't it? I mean, we can see the pattern. It's going to look like this. Except this is a 1. This is a 2. Sorry, this is a 0. This is a 1. 0, 1, 2, 3, 4, 5. This one's going to be negatives. Because when we put a 5 in here to get x to the 10th and a 5 in here to get 10 factorial, this is going to be -1 to the 5th. Now, the easiest way to probably just approach this and show that the second derivative plus the first derivative, the second derivative plus the function equals 0 is let's just find f double prime of x. So what's f prime of x? Well, f prime of x is the derivative of this, right? That's what it is. The derivative of 1 is 0. The derivative of x squared over 2 factorial with a negative out front is going to be minus. We're going to bring the 2 down. We're going to have x. We're going to have 2 factorial. Here, we're going to have plus. We're going to bring the 4 down. We're going to have x cubed. And that's going to give us that over 4 factorial. Here we're going to have minus. We're going to bring the 6 down. We're going to have x to the 5th, right? Subtract 1. And down here we have 6 factorial. Here we're going to have plus. We're going to have 8. We're going to subtract 1. We're going to have x to the 7th. And down here we're going to have 8 factorial. And finally on this one we're going to have minus. We're going to bring down the 10. We're going to have x to the 9th. And we're going to have 10 factorial. But we know what that's going to equal. That 2 is going to cancel that 2. And we're going to have negative x. That 4 is going to cancel. Remember, 4 factorial is 4 times 3 times 2 times 1. So when we cancel the 4 and the 4, we get 3 factorial. So it's going to be plus x cubed over 3 factorial. This, the 6's are going to cancel. We're going to have minus x to the 5th over 5 factorial. Here we're going to have plus x to the 7th over 7 factorial. And finally here we're going to have minus x to the 9th over 9 factorial, and it's just going to keep going. Now remember, that's f prime of x. Our job is to show that when I add the second derivative to the function itself, I'm going to get 0. So let's find the second derivative. I'm going to take the derivative of this. Well, the derivative of x is going to be negative. This 3 is going to come down and turn this 3 factorial into a 2 factorial. So it's the same math we did over here. So I'm going to have x squared over 2 factorial. Here, this 5 is going to come down and turn this 5 factorial into a 4 factorial. And I'm going to have minus x to the 4th over 4 factorial. Here, this 7 is going to turn this into a 6 factorial, and I'm going to have plus x to the 6th over 6 factorial. Here, the 9 is going to turn this 9 factorial into an 8 factorial, and I'm going to have minus x to the 8th over 8 factorial, and this is just going to keep going and going. Well, add these two together. This is a 1 and a negative 1. That's 0. This is a negative x squared over 2 factorial. That's a positive x squared over 2 factorial. 0. This is x to the 4th over 4 factorial. That's negative x to the 4th over 4 factorial. 0. This is negative x to the 6th over 6 factorial. That's positive x to the 6th over 6 factorial. 0. This is x to the 8th over 8 factorial. This is minus x to the 8th over 8 factorial. 0. And it's just going to continue. Term by term by term, they're going to be the same thing. Right? If we wanted to, I mean, if we take a look at this, right? If we take a look at this, this is literally exactly the same thing we have written right here, right? It's this. But it's off by what? A minus sign. This is equal to the same thing we have right there. It's exactly the same thing, term for term for term. They're all the same, except they're opposite in sign. So since f of x is equal to that, and f double prime of x is equal to its opposite, they add to 0. So you can do it term by term, or you can just look at it series by series. All right, I hope those help you work out the rest of the problems in section 8.6. Thanks for watching the videos.